Up to you, Andy.
Great, thank you very much. Thanks, Nick, and thanks, Alex. So I'm going to give a bit of an introduction to the project, and then my colleagues are going to give you a lot more detail. But the project we're talking about is called New Manufacturing Techniques for Optimized Fibre Architectures, and it's really about how do we make particularly 3D preforms for composite materials. How do we improve their performance? How do we optimize their performance? And also, what manufacturing techniques can we develop to make new material forms that give us the properties that we really want? So this is about 3D preforms, so things like 3D woven materials or 3D braided materials. And we know that those materials offer better, in particular through thickness, mechanical properties than you would get from, say, laminated composites. We also know that they can be manufactured to a near net shape. In particular, you can put bifurcations into 3D weaves that allow you to open them out to make things like T-pieces. We know that some of these materials are already being used in industry. 3D angle interlock composites, for example, are being used in the aerospace industry as we speak. But we know that the selection of the right architecture, the right design of the preform is a challenge because you've got an awful lot of variables that you can play with. So how do you determine the right material form, and also how do you manufacture the right architecture? Those are both key challenges. So the key questions we're looking at then is how do you design a reinforcement which is most appropriate for a particular application, considering both the mechanical performance that you want, but also manufacturing consideration, including how easy it is to infuse successfully through a process like resin transfer molding, for example. And then can you manufacture that optimal reinforcement with conventional equipment, things like jacquard looms that are available to produce materials commercially now, or do we need new technologies to give us the material forms that we really want? So in this project then we're taking an optimization approach, and we're really doing this in two ways. First of all, with manufacturing constraints, in other words, looking at material forms that you can make with commercially available machinery and where there are commercial suppliers now, how can we optimize the material form for a particular application by varying the pattern, the weave pattern within a 3D woven material, perhaps the type of fiber, the spacing and weight of the yarn, for example. So that's kind of approach one. But approach two is really to ask the question, what if we relax the manufacturing constraints? In other words, what if we model materials that you can't make with commercially available material manufacturing solutions? What then do you end up with as an optimized material form for a particular application? And then we can consider the development of new manufacturing technologies to realize those new optimum material forms. So really the way that this works is we're optimizing the material form using computational techniques, which I'll come on to briefly, and then our colleagues at Manchester are developing new manufacturing technologies. And the sorts of things you can see on the slide represent the kind of areas where we're developing new manufacturing processes. Prasad will talk a lot more about this, but we're looking at things like multi-axial woven materials, where you don't just have 0-90 yarns, but you have yarns at any angle that you like in the plane. That's one of the technologies being developed. And another is cylindrical materials with through thickness reinforcements derived from a combination of a braiding and winding process. So final slide from me before handing over to colleagues to give the details. This kind of works in partnership between Nottingham and Manchester. So the team at Nottingham are working on the optimization and the modeling side of this. The team at Manchester are working on manufacturing. So for modeling, we generate models using our TextGen software for the material form that we're interested in. We predict the material properties of that model. So for example, the mechanical properties of a composite with that reinforcement inside it, but also the permeability, infusibility, if you like, of the material as well. And we can do all of those things automatically, and we put those into an optimization framework that lets us determine the optimum material form. And then colleagues at Manchester are developing manufacturing techniques to help us to realize some of these optimum forms. And they're looking at two options there, techniques derived from weaving and techniques derived from braiding or winding. And Prasad will say more about those in the next presentation. And then finally, we're applying all of that to some demonstrator components. And those are a vehicle floor pan, which has been supplied to us by the AMRC, and also a pressure vessel that's been supplied to us by Luxfer. And with that, I'm going to stop and hand over to Prasad.